I'm Eduardo Corpeño, and I'd like to invite you to take this course where we will create a neural network from scratch in Python. Whether you are starting your journey into artificial intelligence and machine learning, or you have some experience using neural networks with popular tools like PyTorch or TensorFlow, and you'd like to brush up on the basics, this course is for you. Although professional tools allow you to train neural networks from a high-level perspective, the objective of this course is to give you a chance to tap into the details of the algorithms behind neural networks. This will allow you to fully understand what's going on inside, and you'll make much better use of professional machine learning tools in the future. So come join me in my LinkedIn Learning course, and let's have fun with neural networks and Python. First and foremost, you must feel comfortable with writing code in Python 3. If you're not sure, I suggest that you give it a try until you reach the first programming exercise. If you still need some training, go ahead and browse our library to choose one of our many courses on Python. Second, you may run the exercise files using a GitHub codespace, which is a nice cloud development environment for you to test your code without having to install anything. We'll tell you more about this later. In case you prefer to run the code in your computer, you'll need to have Python 3 installed with the NumPy library. Also, for the final project, I will show you an application with a graphical user interface that uses the tkinter package, which probably came with your Python distribution. In the GitHub codespace, you will use the cloud version of Visual Studio Code, but I also recommend
how to work with LinkedIn Learning courses using GitHub Codespaces. Codespaces is a code editor in the cloud with the full power of Visual Studio Code. It allows for real-world hands-on practice that mirrors software development in the workplace. This course was created using GitHub Codespaces. Using Codespaces, you have everything you need to get going without needing complex installations or build tools. One click, and you're ready to go. To practice along with the course, you can create a codespace directly from the course overview page. First, click Open next to GitHub Codespaces. If you're already logged in, you'll be directed to a Getting Started with GitHub Codespaces page. If you're not logged in, you'll be prompted to log in or create a free GitHub account first. From this page, click on Create Codespace on Main. The first time you open up a codespace, it might take a few minutes to create the virtual machine. Once it's done, you'll enter the code editor environment. If you're familiar with Visual Studio Code, this is a special version of that editor running on GitHub's servers. Your course can have one or more extensions pre-installed based on the course you're taking. Those can be found in the Extensions panel. Because this is a browser, it's easy to inadvertently close the browser window and lose the editor. If you do that, don't panic. Codespaces saves everything you're doing on a virtual machine. You can always get the code space back for this repo right here. Notice that it even remembered that I had opened the Extensions panel. An alternate way to create a codespace is directly from one of our course's GitHub repositories. From here, click Code and then Create Codespace on Main. You can also restart a previous codespace from this location. GitHub Codespaces is compatible on devices with smaller screen sizes, like mobile phones or tablets, but it is optimized for larger screens, so we recommend that you practice along with this course on a laptop or desktop computer. The sample course I'm looking at is what is known as a flat branch repository. You can tell because there's a single branch when you click on the branch icon on the status bar. You can also tell because there are different folders for each of the videos in the course. This is a sample of what a multi-branch repository looks like, which is more common when you're working with web frameworks. If you go to the branch icon on the status bar, you can see that there's more than one branch. You can switch to the different branches using this menu. The branches are named with the chapter and the video number you're watching. If you see a B at the end of the branch, that's how the code looked at the beginning. If you see an E, that's how the code looked at the end. Let's switch to how the code looked on chapter 2 and the third video. I'll choose the beginning branch. As you work through a course, you might make some changes on a branch. I'm going to make a minor edit on the index.html file right here. I'm going to go ahead and save that. And you can see that I've modified this file because there's an M right here, and the branch name now has an asterisk on it. If I try to switch to another branch that causes major changes, like say 0703E, I may see a dialog box like this. If you don't care about saving your changes, you can simply hit the Force Checkout button. It will let you switch to that branch. You can then choose to discard the changes on this file. Your instructor will let you know what the folder structure is for your course. Forking lets you create your own copy of the repository on your account so that you can keep any changes that you've made, even if you've deleted the code space. To create your own fork, you can click on the fork button on the repository. I'm going to hit Create Fork. I don't have my own copy of this repository, and if I want to, I can start a new code space on that fork. This forked version is almost exactly like the original repository, but it will let you push your own changes. Notice that the URL of the repository is slightly different.
A neural network is a piece of software. It's a model of the brain, and like so, it's capable of reproducing some behaviors of the brain, like learning and classifying. That is, it can be taught to recognize the category of a set of things you present to it. For example, telling the difference between apples and oranges in a picture. Now let's consider what a neural network is not, so that we get some misconceptions out of the way. A neural network is not a series of if-then statements or any other form of hard-coded data the software may fetch to produce an answer. A neural network is not all there is to machine learning. In fact, you'll see that machine learning is an extensive field of knowledge on its own. And lastly, although neural networks are useful for classifying, they are certainly not the only type of classifier out there. Now I'd like to give you an idea of what constitutes a neural network. Simply put, a neural network is a collection of neurons, which are small computing units that perform So here are some of the most important aspects about Python I'd like you to know. First, Python is undoubtedly one of the most popular programming languages today. It has a very convenient syntax for machine learning, especially because of the mathematical capabilities already embedded in the language. There are lots of libraries available for pretty much any application in machine learning, and this includes lots of neural network variants. Lastly, Python is a very friendly language when it comes to porting your code from one platform to another. So I feel pretty confident when I say that you'll be able to run your code anywhere. That's why I don't expect you to have any platform-related trouble when setting up your environment or trying out your code. I'd like to tell you just a few of the most popular applications of machine learning, which is the field of computer science related to training machines to solve problems. Machine learning algorithms are widely used for image recognition, where a machine can be taught to make sense of still images or video. An example of this would be face recognition in surveillance systems. Speech recognition is something you may already be used to. Well, this is another typical application of machine learning, where the input from thousands and thousands of people has taught a machine what their words mean over time. These people may have different voices and accents, and this makes the computer even better at understanding what new people are saying. Prediction is a big application of machine learning, which is useful at producing stock market advice, weather forecasting, and even at many stages of healthcare, like diagnostics and treatment. Another big application of machine learning are recommender systems, which I'm sure you are experiencing all the time in your video services like Netflix and Amazon Prime Video, in online stores like Amazon.com, and even in the advertisements you get in social media. These systems don't only learn from your product feedback, whether you liked a product or not, or how many stars you gave to it, but also from your purchase or view history, and from the data of people who behave like you. Finally, an example of machine learning I like very much is Akinator.com, which is a genie capable of telling who or what you're thinking of by simply asking questions to you. A similar one is 20Q.net, which plays the game 20 questions against you. You should try these too whenever you get bored. They're surprisingly good. Now let me briefly tell you about the three broad paradigms of machine learning and some of their best-known tools. First, we have supervised learning, where you actively teach the AI by providing it with lots of data samples along with the results you expect. Here are two big problems supervised learning can solve. Regression, where the AI comes up with the continuous function that behaves like the data you provided. I'm talking about tools like the linear regressions you may have used in spreadsheets. This is useful for making stock market predictions and weather forecasting. Next, we have classification, or recognizing the category a sample belongs to. Among other famous tools, we have the support vector machine, neural networks, and decision trees, which are very suitable for implementing the software behind Akinator.com and 20Q.net. The second paradigm of machine learning is unsupervised learning, where you simply feed data into the AI and it makes sense of this data on its own. Among unsupervised learning tools, we have a big family of clustering algorithms to divide samples into clusters, thus learning from the data. This applies to medical imaging and recommender systems. Anomaly detection systems are capable of finding uncommon samples So let me show you a few classifiers in machine learning and where neural networks fit in. First, we have the logistic regression, which is a function with an input vector and a single return value. Depending on the values in the input vector, the function will return a value between 0 and 1 as a way of classifying the input as belonging to class 0 or class 1. This classifier is technically a very simplistic neural network known as a perceptron. We'll take a detailed look at perceptrons shortly. Another type of classifier is the k-nearest neighbors algorithm. To understand how it works, suppose that we plot our samples in a 2D plane so that we have some samples that belong to one category shown as squares, and some other samples belonging to a second category shown as triangles. This algorithm takes in a new sample of an unknown category, shown as a circle near the center, and classifies it in the same category as the majority of its k-nearest neighbors. To avoid ties, k must be an odd number, and even so, its value is very crucial. For instance, suppose we chose k equals 3 for this plot. Then the new sample would be classified as a triangle because most of its neighbors are triangles. However, if k equals 5, then it would fall into the square category. That said, the advantage of this algorithm is its evident simplicity. There are very few calculations going on. Support vector machines are very similar to neural networks in their input and output structure, and they often solve the same problem. Take this plot, for example. A support vector machine is capable of finding the line that acts as a boundary between the two categories of points shown as squares and triangles, respectively. This boundary is a line for this 2D example, but in general it's known as a hyperplane. So here we have a valid boundary with a potential inconvenience. It's too close to some samples. Here's another boundary that's way too close to some samples. One of the most useful features of support vector machines is that they are capable of finding something close to the optimal boundary. That is a line that separates the categories while maximizing its distance to every point in the plot. Here's an example of such boundary. A seemingly different approach to classification are decision trees. These algorithms have a tree-like structure of questions very much like a series of if-else statements, but not quite. It turns out that a decision tree uses a training algorithm based on information theory to produce the shortest possible tree. That is, to classify a new sample in the smallest number of steps. In the illustration, we have a decision tree to determine whether a passenger of the Titanic survived or not. This tree was produced by observing data and noticing that most of the survivors in the Titanic were women and young children with not so many siblings. It's not perfect. It may fail sometimes. extensive set of tools for pretty much any problem out there. Now let's zero in on neural networks. There are dozens of neural network types, but I'd like to mention three very special types. First, we have hop-field neural networks, which have a fully connected architecture. That is, every neuron in the network sends its output to all the other neurons. It does have inputs and outputs. The inputs modify what's going on inside the network, including the output values. The logic behind this architecture is to let the neurons collectively perform the necessary computation in an emerging manner. That is, the individual neurons aren't aware of the big picture, but we can influence the whole network to produce the outputs we need, given the inputs we feed into the network. Perhaps the best known category of neural networks is the feed-forward model, where we have a set of inputs, a series of layers of neurons, with signals propagating forward until they reach the output. The success of this type of neural networks led to the development of a large family called deep neural networks, which have a large number of neuron layers between the input and the output. One example of this evolution of deep neural networks are convolutional neural networks. An application I like very much is the Deep Dream Generator, which is a convolutional neural network that takes in a picture as input, then processes it through the many layers it has, and finally shows you the modifications it has added to the original picture. These modifications include information it has collected over time from thousands of pictures it has seen before. So it seems the AI has been dreaming with your picture, distorting it with interesting imagery in the process. Here we have a nice picture of my dog Nicolas, and this is the dream it caused. Notice the multilayer perceptron. This is the best known feed-forward neural network, and it's one of the oldest models of the brain. It consists of neurons organized in layers, and the data traverses the network from input to output. This is typically sketched from left to right. Feed-forward neural networks have a so-called fully connected architecture between layers of neurons. Here's an example. First, we have the input layer. It contains the inputs of the network, technically known as the input vector. This is the only layer that does not contain neurons. You can think of these elements as input terminals. This is important, especially for the implementation, so I'll say it again. You don't have to place neurons in this layer. Second, we have the set of hidden layers, which are composed of neurons. Notice how all neurons from the first hidden layer are taking in all of the inputs from the input layer. The second hidden layer is composed of neurons that take all of the outputs from the first hidden layer. This is what fully connected means in this context. These layers are called hidden because the neural network does not expose them to the outside world. The outside world modifies the behavior of the network through its inputs, and the so it makes sense to take a quick view at the ultimate computer. There are many things we know about the brain, and so many other things we don't. Here are some important things we do know. The brain is made of neurons. The brain is a biological neural network. Each neuron in the brain performs a very modest cognitive function, contributing to larger cognitive functions. Finally, the combination of these cognitive functions results in our brain's mental ability. Everything the brain does is the result of these tiny computations. Feelings, memories, movement, speech, dreams, all of it. So let's take some of the known facts of neurons to come up with a computational model of a biological neuron. The structure of biological neurons consists of several parts. We are only interested in 3 parts of the neuron. Dendrites take electrical signals coming from nerves or other neurons. These signals may come from sense organs like the eyes, tongue, or ears. The nucleus of the neuron is where some processing is believed to happen, so that the combination of inputs can yield some response. This response is usually interpreted as binary, so that if the stimulus from the inputs is high enough, it is said Let's just assign those roles to a set of inputs, a calculation unit, and an output, respectively, to come up with the block diagram you can see at the right. We'll call the inputs x0 through xn-1 for a neuron with n inputs. Now, biological neurons seem to react in different sensitivities to different incoming signals. So we'll model that mathematically by assigning a weight to each input channel. Let's call them W0 through Wn-1. Next, the computation performed in order to fire or not is a simple weighted sum, as shown inside the circle. And that's exactly what our output will be. Here's an example of how a neuron would help us classify. Let's suppose we have a 2-input neuron and we feed data with 2 features into it. These features are shown in the plot at the right, which shows the risk of getting some medical condition X based on 2 factors, A and B, as the horizontal and vertical axis. Each point represents a person, and its shape represents that person's risk of getting that medical condition. Triangles are at risk, while squares are not at risk. Let's say these points come from a number of observations in a research study. Now let's suppose we want to predict if a person is at risk of getting that medical condition X based on factors A and B alone. We could feed A through x0 and B through x1 into our neuron, and it will give us some useful information. Notice that the weights I assigned to the inputs are 1 and -1. This means that the boundary that divides positive and negative output results would be this line. Take a moment to look at this line and notice that whenever A is greater than B, that is, for a point above the line, the result of the weighted sum will be positive. And whenever B is greater than A, meaning that the point is below the line, the weighted sum will be negative. So this neuron model is indeed capable of classifying if we interpret the sign of the weighted sum as the category. This way, a positive result means that the person represented by A and B is at risk, while a negative sum means that the person is not at risk. Now, although this neuron is capable of producing a boundary line, it's very limited. That's why we need to talk about bias inputs. So as you noticed, a weighted sum is a linear function. It has a weight assigned to each input, which will provide a slope to the boundary. However, an additional independent input is needed to move the line vertically. And this extra input is usually fed a constant value of 1, but it has its own weight. Now let me show you why we need a bias term. The neuron we've considered so far is only capable of producing boundary lines that pass through the origin, or the coordinate 0, 0. So consider this plot where we have a set of students who passed or failed some class. And we want to classify other students based only on their grades on 2 exams in that class, even though there was more graded work. The squares passed and the triangles failed. Our first attempt of a neuron could produce any line with a positive slope, like this one. But notice that, try as we might, there's no way of dividing the 2 categories with a line like this one. How about inverting the slope by switching the signs of the weights? Well, we would get a little closer because the triangles and squares seem to be separated by a negative slope line. But again, stick to the origin and there's no way of placing the line between the categories. As you may have already guessed, a simple solution is to add a bias term, a term that's independent of the grades of exams 1 and 2. Technically, this is the intercept in the equation of a straight line. Notice how this line does the trick for us. None of the previous attempts would have divided the So let me tell you what's wrong with weighted sums. There are 2 inconveniences I'd like to mention. First, values aren't constrained, so a sum may sometimes result in a very large value or a very small value. Second, a weighted sum is a linear function, so the threshold to fire is not very well defined. That is, a change between true and false is not very notable. And, most importantly, it's not easily trained. It turns out that other functions that make learning easier are nonlinear. This is the real reason to add an element to our neuron. So what's wrong with having a very large and a very small value? Consider this example where we have a 2-input neuron and we are feeding 1000 to x0 and 2 to x1. For now, let's leave the bias weight at 0, so the bias is not shown to keep the diagram simple. If we run the neuron, we'll have a result of 2006. So notice that although the weights are very similar, 2 and 3, the big difference in the input values has made the neuron very sensitive to x0 and insensitive to x1. That's the job of the weights, not of the inputs. And what's wrong with linear functions? Well, consider this neuron with one feature input and one bias input. At the right, we have a plot of the output as a function of x0. Now, this is not the usual 2D plot we have seen so far. The line is not the boundary. This plot is showing the output sum z as a function of x0, so the boundary is the horizontal axis. Remember, this neuron will classify the input values as one of two categories based on the sign of the output. That means that whenever x0 is greater than minus 1.25, the output will be positive, putting x0 in the positive category bucket. On the other hand, whenever x0 is less than minus 1.25, it will go to the negative category bucket. A somewhat inconvenient detail of this type of function is that close calls don't have a very dramatic difference. For example, if x0 is minus 1.26 and increases by a small amount to minus 1.24, the category will change from negative to positive, but the value of the function will be close to 0 either way. A more dramatic change in these cases would give us a bit more confidence in the classification. Once again, the real reason why linear functions are inappropriate for a neuron is that this dramatic distinction between the categories near the boundary will make it very easy for this neuron to learn. So in conclusion, we need a nonlinear element in our neuron. That's achieved by adding a so-called activation function to our model. And we'll do that by simply plugging this function to the output of our model so far. This means that the sum will be sent as an argument to the function g. So let's do a quick recap on activation functions. These functions model the desired dramatic threshold behavior of the boundary. They usually constrain the output values, and most importantly, they provide nonlinearity to the neuron, thus enabling training by backpropagation, which is the method we will use. This requires activation functions to be differentiable. So let me show you some popular activation functions. First, we have the binary step function, which limits the output values between 0 and 1. Actually, outputs are exactly 0 or 1. Here's the expression for the function. So as you can see in the plot, the function returns 1 for positive values of x, and 0 for negative values of x. There's the dramatic distinction in the boundary. The function jumps between 0 and 1. Next, we have the logistic or sigmoid function. This is the one we'll use in our neuron. This one also limits the output values between 0 and 1. However, output values are real numbers between 0 and 1. Here's the expression for the sigmoid function. As you can see in the plot, this function has a smooth change in the boundary. And it turns out that its derivative is a very simple function which we will need for the learning part. This is definitely a keeper. We also have the hyperbolic tangent function. This function limits the output between minus 1 and plus 1. Output As you can see, it has a set of inputs with a global bias term. This input vector will go through a weighted sum, and this value will go into our sigmoid activation function. Once again, pay attention to the numbering. The inputs and their weights are numbered from 0 to n-1, and the bias is treated as input number n. So how should we interpret the output values of our neuron? Well, the output comes from the sigmoid function. Notice that the output is greater than 0.5 for a positive input, that is, for a positive weighted sum. This way, an output value of 0.5 seems like a reasonable threshold for firing. So before we dive into the code, let me point out some implementation notes. All values must be real numbers, not integers. The weights and inputs may be implemented as one-dimensional vectors. In our case, we'll use NumPy arrays. This way, the weighted sum may be calculated in one operation as the dot product between the two vectors. That's one line of code. Finally, we'll feed the weighted sum to our implementation of the sigmoid function. Before we get to the code, let me show you how to set up a code space and browse through the branches in Visual Studio Code. Here we have the GitHub repository for the course. To start a code space, you can click on the Code button and go to the Code Spaces tab. Here, you will see a list of your existing code spaces. You may start a code space by clicking on its name to continue where you left off. If this is your first code space in this repository, you can create it by pressing the Create Code Space on Main button. Let's do that. This will open a tab to set up your new code space. Setting up a code space may take a while, but only the first time. Reopening an existing code space is much faster. After booting up, you will see the web version of Visual Studio Code with access to the repository. As you can see in the Explorer pane at the left, there is no source folder. That's because we are in the main branch, which has no code. This is a multi-branch repository, so to access the exercise files for a specific video, you must switch to its corresponding branch. You can do that by clicking on the branch symbol at the bottom. Notice that it reads main. When you click on it, you will see a drop-down menu where you can select a branch. The branches in this list are named with the chapter number followed by the video number. This is the fourth video in chapter 2, so its branch name must be 0204. Now, some branches are provided in the state shown at the beginning of a video as well as at the end of it. These have a letter B or an E at the end of the branch name. So for this exercise, I will pick branch 0204B, as in beginning. Look at the folders at the left. Now we have a source folder. Let me expand it and open the mlp.py source file. Now let me get the bottom and left panes out of the way. So here we have the first part of our perceptron class. First, we have the header for the constructor in line 9 to create a new perceptron object with a specified number of inputs and a bias term, which will be 1 by default. The only member data we need for this class are the weights and the bias term. So let me initialize the weights as a random array of floating point numbers between -1 and +1. This random initial state will be important for the training phase. I decided to use NumPy arrays here. That's why I imported NumPy as NP at the top. So I'll do this with the random function in NumPy. Ready for your first challenge? Let's finish up the perceptron class. First, in order to test the class, we'll need to be able to set the weights at specific values. So we need a method for that, and you can find it in line 21. Just replace the pass statement in line 23. And also remember we'll use a sigmoid as the activation function. So that's the second thing you'll have to write starting at line 25. Again, do this by replacing the pass statement in line 27. So once again, your task is to write two class methods, the sigmoid activation function and a separate method to write values to the weights. For the argument, receive a regular Python list of floating point numbers. You may or may not validate. Here we have my solution. Both methods are one-liners. First, let's look at the setWeights method starting at line 19. As you can see in line 21, I'm simply assigning the NumPy array version of the argument to the class's weights. Now let's see the sigmoid method starting at line 23. As you can see, the sigmoid is simply written as the definition we saw earlier, and I used the NumPy exponential function for this. That's it. Now we are ready to test our neuron. But first, let's give some meaning to our test. Simple functions to see if they were capable of performing the calculations they were designed to perform. This led to implementing logic gates with perceptrons. So let's take a look at a two-input AND gate and its truth table, which summarizes its behavior. Supposing 0 means false and 1 means true, the gate outputs true only in the case where both inputs are true. You may already be familiar with this, but let's look at it from a totally different angle, as a classification problem. This plot shows 4 data points. The coordinates of these data points are the values of inputs A and B. Notice that the data points show their category as a 0 or a 1. This way, a two-input classifier may come up with a boundary that divides the categories. So based on this, a perceptron may behave as an AND gate. Let me show you how the classification is possible. The boundary we are seeing in this 2D plot is technically the line where the sigmoid is 0.5. Now, a 3D plot may help making this explanation better. So let's add a third axis, now vertical, to express the output of the sigmoid. This will be the category that the perceptron has inferred. So if we apply the sigmoid, all of the data points will be a part of the surface of the sigmoid, like objects lying on this uneven terrain. So once again, the height of these objects finally determines the category the perceptron assigns to them. The decision plane will be located at the middle of the sigmoid. So here is a valid implementation of a two-input AND gate. It's a two-input perceptron with the following weights: 10 for both inputs and minus 15 for the bias. I just came up with these weights by aiming to get a negative sum for a result of 0 and a positive sum for 1. After testing it with my perceptron class, I got the values shown in this table. Notice that I included a column for the weighted sum z. Those were the values I was aiming for with the weights I used. So as you can see in the y column, the top 3 values are very close to 0, so they may be safely rounded to 0. And the last value is almost 1. So here's how I test. Ready for your next challenge? Your task is to make your perceptron behave as a two-input OR gate. Here's the truth table for the OR gate, and this is what the classification problem looks like. So to be clear, what you need to do is come up with a combination of weights that will make the perceptron behave as an OR gate. It may help to fill out the Z column of this table first. Remember, you want a negative sum whenever you want the output to be 0, and a positive sum for 1. Go ahead and tweak the code to test your new OR gate. This shouldn't take you more than 15 minutes, especially because you may use the provided code, which is a modification of the AND gate code you just saw. Here we have my solution in line 30. The values I came up with are 15 for both inputs and minus 10 for the bias. This way, any input value of 1 will make the weighted sum positive. Let's see it working. Looking at the terminal at the bottom, we can see the OR behavior. That is, for an input of 0, 0, we get an output value very close to 0. The rest of the input combinations yield an output greater than 0.99. If you like this exercise, you may want to create the NAND and the NOR gates next. Great, so our perceptron can operate as we ask with the weights we write into it. Now we are ready to teach a behavior to our perceptron. Why perceptrons work as classifiers. Let me tell you what it is. Looking back at the pass or fail example, this situation is suitable for a perceptron because it is linearly separable. Simply put, linear separability is a property of a dataset with two categories where a linear function can separate the categories. This is a 2D plot and there is a straight line that separates the categories. Therefore, this example is linearly separable and a perceptron can take care of it. For more dimensions, a plane or hyperplane would separate the categories, but it's still a linear function. Let's look at a pesky logic gate example. The XOR gate outputs 1 when only one of its two inputs is 1, but not both. Look at the 2D plot. I dare you to find one single straight line that divides the zeros and the ones. Did you find it? Of course not, because there is none. The XOR problem is not linearly separable, so it's impossible to solve it with a single perceptron. See what I did there? I chose my words carefully. We cannot implement an XOR gate with one perceptron, but we can implement it with 3 perceptrons. Let me show you how. Recall the OR gate. This gate takes care of the first 3 XOR cases in the truth table. Look at the 2D plot of the XOR gate. If we used an OR gate, we would get all but one of the points correctly classified. The top right point should be 0, but the OR gate would classify it as 1. What about a NAND gate? This one gets the last 3 XOR cases right. If we used a NAND gate to classify the XOR cases, we would misclassify the bottom left point. See where I'm going? If we could somehow combine the OR gate with the NAND gate, we would get an XOR. Well, almost. We still need some simple logic. Look at the overlap between the 2D plots. We want to classify as 1 only the points that get classified as 1 by both gates. So the AND gate would do the trick. This isn't anything new though. This is a well-known implementation of the XOR gate, a composition of an OR, a NAND, and an AND gate. Here's the schematic of such composition. So this looks like a plan. Let's create a network of 3 perceptrons. Multilayer perceptron. Think about it. It's made of perceptrons, they are interconnected in a feed-forward fashion, and they are organized in layers. This is the input layer. Remember, no neurons, just the inputs. This is the hidden layer with 2 neurons, and this is the output layer with just 1 neuron. So it's time to start writing code again. So here's our first implementation of the multilayer perceptron class. I'll write the constructor, and you'll write the rest. In the constructor, starting at line 36, I'm receiving a parameter called layers, which is a Python list of integers which represent the number of neurons per layer. This includes the input layer, which has no neurons, but here we mean the number of inputs. The other parameter is the bias, with a default value of 1. Now let me show you the data members of the class, starting at line 38. The layers list becomes the layers numpy array, with exactly the same data as the parameter. The bias is also a member. Now in line 40 we have the actual network. It will be a numpy array of numpy arrays at the end, but for the moment I'll use a list of lists, mostly because I'll create arrays of different sizes. And lastly, we'll need another array with the same dimensions as the network to hold the output values of the neurons. This will be useful for propagating the results through the network. The next part is where I'll write some code. It consists of two nested loops to create the neurons layer by layer. The outer loop iterates on I for each layer. So for each layer, we need to have a list of values and a list of neurons. The new list of values will be filled with zeros for every neuron in the layer. Now the inner loop iterates on J for each neuron in the layer. Are you ready for your next challenge? Now you must write two methods so we can test our multilayer perceptron. First, we have the setWeights method in line 56. For the winit argument, you may use the organization you want, but I suggest that you make it capable of initializing a network of any size. Don't forget the bias weights. Also notice that I have written a printWeights method starting at line 61. This is for you to check if your neural network received the weights correctly and to see the weights when you have trained it later in the course. And lastly, we have the run method starting at line 68, which feeds a sample to the network and returns a NumPy array with the output values. Let me tell you what to return just to be clear. We simply return the last element in the values array, which is a NumPy array containing exactly the output layer values. So to recap, you must write a method to write values to the weights and the Here's my solution. For the setWeights method starting at line 54, I'm implementing winit as a list of lists of lists. That's 3 dimensions. And that's because I'm specifying the layer, the neuron, and the input associated to each weight. However, winit will have one less entry in the first dimension because I'm not specifying anything for the input layer as it has no neurons. So I implemented 2 nested loops starting at line 57. The outer loop iterates I through the layers in the network, and the inner loop iterates J through the neurons in each layer. Now, inside the inner loop, I'm using the setWeights method for each neuron. Notice that since winit doesn't have anything for the input layer, I am indexing the network array at I plus 1. Now let's look at the run method starting at line 68. So here, the first thing I do is turning X into a NumPy array. Then I copy X into the first layer of the values array. Now it's time to run a 2-level nested loop for every layer in ascending order, and every neuron in each layer. The body of the loop is simply running the current neuron by feeding it the values in the previous layer. That's it. Now we are ready to run a test on the whole thing starting at line 79. So first, we create a multilayer perceptron with the dimensions of the XOR gate design. Next, I'm assigning the required weights. These are the weights It's time to talk about the need for training. So let's look back and reflect on the following points. Throughout the coding exercises of this course, we haven't seen a useful neural network yet. True, we have seen networks that behave like gates, and they may be useful. But there are much better hard-coded alternatives to perceptrons when it comes to implementing a NAND or an XOR. For example, we could simply use the logic embedded in programming languages to get away with logic. Well, it turns out that the real value of neural networks lie in their ability to learn. Sure, we just got a multilayer perceptron to behave as an XOR gate by writing the exact weights it needed. But what if we could show the neural network a lot of examples of how an XOR behaves so that it can learn from those examples? Wouldn't that be something? So I have good news. Up ahead, we'll see an algorithm to train multilayer perceptrons known as the backpropagation algorithm. So sit tight and pay attention. But wait, there's another reason to train a neural network. Remember linear separability? Well, I have bad news. Linear separability is hardly a given. Consider this example of classifying things as small or large based on their length and width. Let's say that small is represented by triangles and large is represented by dots. Moreover, notice that this is not linearly separable. There is no straight line that will divide the two categories, but that doesn't mean that a single perceptron won't do a good job at classifying these samples. Take this line for example. Notice that it will misclassify one dot and two triangles, which doesn't seem so bad. And even if we used a multi-layer perceptron, we will get a nonlinear boundary like this one, which does a better job misclassifying only one triangle. It's better, but it's not perfect. And that's the whole point of training. We are looking for a model that will get most of the samples correctly classified because we don't know so much about the problem, and we are basing our judgment on the samples we have seen. This brings me to the problem of generalizing. This neural network may work very well for the provided data points, but it still has to prove useful for new data it hasn't seen before. So let me tell you about 3 situations in the spectrum of misclassifying and generalizing. Here we have a different dataset for the same problem we just saw. I'm showing you the same plot 3 times because I want you to compare these 3 situations for a classifier. So look at the leftmost plot, and suppose we use a single perceptron with a straight line as boundary. As you can see, this one misclassifies 2 dots and 5 triangles. This situation is known as underfitting, where the network misclassifies too often, so it's not very accurate. So we don't want this. This is bad. Now look at the middle plot. Suppose we use a multilayer perceptron that ends up using an arc as a boundary. Notice that the misclassification has dropped to 1 dot and 2 triangles. Now these numbers aren't as important as the visible shape of the trend between the categories. When we train a neural network, we are aiming for a boundary that works just right. That is, it rarely a usual top-level procedure I'll briefly describe to you. But first, let me tell you what a dataset is. First of all, a dataset is a collection of samples that contain features and labels. We usually represent features with X and labels with Y. The input signals for the network are known as features because what you usually feed a neural network are features of a data point which can be represented as numbers. For example, length, height, price, salary, number of rooms in a house, blood sugar level, and so on. The labels, on the other hand, are the known category attached to each sample. This is how we teach the network. We show the samples to it. And finally, the network is able to learn with each feature label pair. So here's the usual training process. You typically want to use 3 datasets: a training set, a validation set, and a testing set. The training set is used to train the network so that it learns all it's supposed to learn. This is important, so I'll say it again with different words. This is the only dataset that will be used with the training algorithm. The other 2 are used for 2 rounds of assessment. So we run the training set with the training algorithm. Another important detail is that we have to run the training set lots of times. Each time we run the training set with the learning algorithm is known as a training epoch. Well, the training process usually involves hundreds or thousands of training epochs. We stop after some number of epochs or until some error metric drops under a desired value. We'll talk about this error metric in a bit. After that, the neural network will have learned something from the samples. The validation set is used to assess how well our neural network has learned as compared to other competitors. There's nothing we intend to do to improve the learning. Actually, what's usually done here is that we prepare several classifiers, say 2 support vector machines, and 3 neural networks. We may tweak our network, you know. We could use one with 1 hidden layer and another with 3 hidden layers. We may also vary the number of neurons per layer, and we may use different activation functions, for example. So we train all of the competing classifiers. And then we feed the validation set to all classifiers. This time we only run the dataset, we don't train the classifiers. The validation set will allow us to rank our classifiers and choose the one that shows the best performance for us. Let's say that's our neural network A. Lastly, the testing set is used. So let me tell you what I meant by that. An error function measures how bad a classifier is doing. So a large value is bad and a small value is good. This function is essential in the training process. So up ahead we'll learn about a training process called gradient descent. Throughout the algorithm, we'll calculate two types of error metrics, one for the output of a neuron and one for the whole network. So the first metric is not formally known as the error because it's just the measure of how far off a neuron is from the expected value dictated by the label in the dataset. It's simply a subtraction. Let me show you. Suppose we enter a sample xy to a neural network which for now will be a single layer perceptron. Now suppose that the output of this one output network is 0.6. And let's say that the label for that input sample is y equals 1. This way, the error or deviation can be calculated as the subtraction y minus out. Again, this output error is just a step in the calculations, but it will show up quite often. So the point is that the training function must somehow contribute to getting out closer to y over time. That is, making the error approach 0. Now, when we are assessing the performance of the neural network, we use a metric known as the mean squared error. There are several important details about this function. The error is calculated as the sum of the squared output errors for all neurons in the output layer, all of this divided by n, the number of neurons in the output layer. Remember, a neural network may have more than one output. Since we'll use this error to check how our Let's talk about the general algorithm known as gradient descent. This is a training method to minimize the error of our neural network. It consists on adjusting the weights in order to find the minimum error. To get an idea of the logic behind gradient descent, think about trying to go downhill to the lowest valley in the error function. So here's a graphic aid to understand what gradient descent is all about. For now, suppose we have a neural network with several weights, but we are only interested in modifying one weight to see how it affects the overall error of the network. So let's say we get this function and we set this weight to, say, this value. Now think of evaluating this function as placing a marble over the function, like this. Reducing the weight will get us to a higher, thus worse error. But increasing the weight will lead us downhill. If we keep increasing the weight, we'll eventually reach the lowest point in the plot. That's our objective. This is the global minimum of the function, and that's the best error we can get by modifying this particular weight. So in some sense, we want to simulate gravity in this plot, and that's what gradient descent will do for us. Now let me quickly warn you about a possible problem here. Since we don't know what our error function will look like, and we initialize our weights randomly, what would happen if we start with this value for the weight? Well, simulating the same gravity effect with gradient descent, we would move the marble to the left, eventually getting stuck in this valley, which is not the global minimum, but a local minimum. Don't worry, there are several methods to overcome this local minima problem. Pushing our example a little forward, think about modifying two weights to manipulate the error. This would give us a 3D plot where the height is the error, and the two weights will place the marble at different points in this It's a simple update formula for adjusting the weights in a single perceptron, that is, a neuron. Yes, it's a simple formula, but its reasoning is very clever. The delta rule considers the following values: the output error, this is the simple subtraction error, one input, the one affected by the weight we are going to tweak, and a constant known as the learning rate. So here's a nice equation to calculate the update in a weight I in a neuron k. Let's call it delta W sub ik. And it's the value we'll have to add to W sub ik to get the boundary closer to what we want. So, to calculate this delta, we multiply the learning rate eta times the output error. That is the label y sub k minus the neuron's output O sub k times the ith input value x sub ik. Yeah, it's very simple, but notice what's happening there. The output error will be positive if the label y is higher than the output, and it will be negative if y is lower than the output. This means that when we later update w, it will contribute to making the output closer to the provided label. If we calculate all of the delta w's and add them to the w's, our perceptron will be one step closer to having the boundary we want. So let me tell you a few things about the learning rate. First, it's a unique constant in the neural network. There's only one learning rate for all neurons. As the name suggests, it directly affects the rate of learning because higher values will result in larger leaps for the weights, and lower values will result in smaller leaps for the weights. Does a higher learning rate mean faster learning? Yes. Does a higher learning rate mean better? No. The learning rate is usually initialized at 0.5, but you may have to tune it if learning is too fast or too slow. Here's why. Let me show you 6 updates of a weight in this error function considering a learning rate that's too slow. So pay attention to the marble. 1, 2, 3, 4, 5, 6. The marble will eventually find a minimum. It will take a long time, and it may get stuck at the first local minimum it finds. This could be much better. This is a general form of the delta rule. It has several requirements on the neuron model, especially on the activation function. Don't worry, the sigmoid makes it easy. The algorithm calculates all weight updates throughout the network. This is done by propagating the error back through the layers. So here are the steps of the backpropagation algorithm to train a multi-layer perceptron with one sample. 1. Feed a sample to the network. 2. Calculate the mean squared error. 3. Calculate the error term of each output neuron. 4. Iteratively calculate the error terms in the hidden layers. 5. Apply the delta rule. And 6. Adjust the weights. Now, for your next challenge, you'll have to write the backpropagation algorithm. That's why we're going to have a close look at each of these steps because it's easy to get confused. For this example, I'll use a volunteer, which is this network with 3 inputs, 4 neurons in the first hidden layer, 3 neurons in the second one, and 2 in the output layer. In my multi-layer perceptron class, these are layers 0 through 3 respectively. As you can see, our neurons are explicitly showing their bias inputs because we'll use them in the algorithm. But remember that these inputs are rarely shown for the sake of simplicity. The bias is fixed at 1, so don't confuse it with the bias input weights of the neurons. The first step is to run the network forward. So we feed a sample, say x equals 251. And let's say that our network spitted out the output vector O equals 0.2 and 0.49. Our training sample included a vector of labels y equals 0, 1. That is, the expected output for the first output neuron is 0 and 1 for the second one. The second step is to calculate the mean squared error. This needs to be done at this point because we will assess the accuracy of the neural network later, and we are about to change its weights. Remember, the MSE is calculated on the outputs, so we use Y and O. So subtracting vectors y minus o, we get minus 0.2 and 0.51. Squaring those values, we get 0.04 and 0.2601. Adding those values and dividing by 2, we finally get 0.15. That's the current state of the error metric for this network when it receives x as input. We'll use this value later to review how well the network is learning. This is the error function that is undergoing gradient descent. Is 0.15 a large or small error? Bear with me when I say that it doesn't matter. What matters is reducing this number very much as we iterate. Step 3 is to calculate the output error terms. This is a third error metric, and it's an intermediate error calculation that will be used for guessing how bad each neuron is doing. Notice that we're paying attention to the output layer. We'll later use these error terms to calculate the error terms in the hidden layers moving backwards through the network. That's the reason for the name backpropagation. Finally, we'll know the error term for all of the neurons in the network, and we will apply the delta rule to calculate the deltas and adjust the weights. So the error term for neuron k in the output layer is represented by lowercase delta sub k, and it's related to the partial derivative of the error of the network with respect to each weight in that neuron. So delta sub k equals O sub k, that's the output value of neuron k, times 1 minus O sub k, times the simple output error y sub k minus O sub k. Just so you know, this part is the derivative of the sigmoid function, which is very simple, and that's one of the main reasons to use the sigmoid function as an activation function for our neurons. So let's suppose we are interested in calculating the error term for output O1. Now let's zoom into the output layer for this example. To calculate lowercase delta sub 1, that's the error term for neuron number 1 in the output layer, we'll use O sub 1 and Y sub 1 in the equation. It's that simple. The fourth step is where the magic happens. Now we're going to calculate the error terms for the hidden layers, and we do this backwards. The previous step was done in the output layer. This step iterates from the last hidden layer all the way to the first hidden layer to find an error term per neuron. Here's the equation for an error term lowercase delta sub h. It's almost the same as for the output layer. The derivative of the sigmoid is still there, but in the hidden layer we have no idea about the error because we simply don't know what to expect from the intermediate neurons. So what we use instead is a sum of a product that includes the error terms in the neurons connected to this neuron's output. These neurons are in the next layer, and we have just calculated their error terms lowercase delta sub k. But that's not all we calculate in this sum. We must multiply these error terms by the weight of the input that's connected to the output of our neuron, h. So let's zoom in again to see what happens in the second neuron of the second hidden layer. This will be neuron 1 in the last hidden layer, so in the equation h will be 1. Actually, by lowercase delta 1, I'm hiding the layer number. So let me be more specific in the diagram and call this lowercase delta 2 1, meaning that this neuron is in layer 2 and it's neuron number 1, the second neuron. To calculate lowercase delta sub 2 1, we'll need the usual derivative of the sigmoid times the weighted sum of the error terms. So these are the products we'll have to add for this neuron. Lowercase delta 3 0, or the error term of the output neuron 0, times W 0 1. That is the input weight 1 of this output neuron. We'll Ready to finish up your multi-layer perceptron class? This time your task is to write a backpropagation trainer method which will run one sample through the network with the backpropagation algorithm. Don't worry, you'll just have to write a few lines per step in the provided code. In fact, you'll just have to fill in the blanks. You can do this. And feel free to go back to the backpropagation videos if you get stuck. The method is called BP and it receives a feature vector X and a label vector Y. Both are regular Python lists. So the first two lines convert those lists into NumPy arrays as usual to have the operations in NumPy. Now your challenge starts in line 87. Notice that I've placed a comment for each step and skeleton code for the loops. Now for steps 3 and 4, you'll need a new NumPy array of arrays I added to the class to store the error terms, or lowercase deltas. That's why I named it lowercase d. You may want to check the constructor code starting at line 36 and look for this array. So as you can see, I have highlighted all the appearances of d in the constructor. And if you pay attention, you'll see that it has the same organization as the values array, so it's created and initialized right next to it. So this d array holds the error term for each neuron, just like the values array holds their output values. Now let's go back to the backpropagation method. As you can see in line 109, we must return the mean squared error because we'll need it in the training process later. Speaking of training, at the bottom I have included a training example starting at line 113. So notice that I'm running the BP method once for each case in the XOR truth table, and that's my whole dataset, just 4 samples. I'm running it for 3000 epochs, and I'm calculating the mean of the 4 errors in an epoch. Notice that I'm only printing the error every 100 epochs, so I'm expecting to see 30 error values. So here's my solution. Step 1 is the simplest. In line 93, we just run X through the network and assign the result to a new array called outputs. Step 2 is where we calculate the mean squared error. So first, I saved the simple errors in an array called errors, and notice that I'm using NumPy vector operations, like the subtraction y minus outputs. Then, the mean squared error is the sum of the values in error squared divided by the number of neurons in the last layer. Step 3 is also done in vector operations, just following the equation. Notice that the result goes to the last element in our D array. Now for step 4, pay attention to the loop starting at line 103. First, I calculate the weighted sum of the forward error terms, and then use that sum for the current neuron's error term. Notice that the outputs are not recalculated. They are fetched from the values cache. All this is assigned to each element in the D array, which contains the error terms. Steps 5 and 6 contain the most code, but it's actually quite simple. I goes through the layers, J goes through the neurons, and K goes through the inputs. That's why it goes from 0 to the number of neurons in the previous layer plus 1, because of the bias weight. And that's exactly what the body of the innermost loop is doing. Look at line 114. If K is the last weight, we calculate the delta by multiplying the learning rate times the error term in that neuron, times the bias term as the input, because, well, that's the input. On the other hand, if it's not the bias weight we are checking with K, then we calculate the delta as the learning rate times the error term times the actual input, which comes from our values cache indexed at the previous layer. That's it. Finally, we return the MSE. So let's see it working. Here we have the results. Pay attention to the 30 error values as they go down. Next, we have the weights. Notice that it came up with something other than the NAND or AND combination we designed earlier, look at the values and signs of the weights. This is surely a logical equivalent of that initial XOR. And finally, we have the truth table at the bottom. As you can see, we are practically getting the XOR behavior, meaning that our artificial brain has learned. It's alive. Now, this is my favorite part of the whole process. This plot shows the learning process for the XOR gate we just saw. I got this data by training an XOR like we just saw, and I copied the 30 error values reported in the terminal. I pasted them in a spreadsheet to finally make the plot. You should try it on your own, and you'll get something very similar. As you can see, the plot shows how the error drops as the neural network learns epoch after epoch. These plots usually show you've learned an impressive number of concepts that will be useful in your journey into artificial intelligence and machine learning. Now it's time to have some fun with a practical application of your brand new Multilayer Perceptron class. The project is a simplified version of optical character recognition, or OCR. So let me tell you a few details about OCR. It's a set of algorithms used to recognize characters in a picture. It's useful for many applications like digitizing books or documents. For example, if you have an old book, a contract, or a printed document you'd like to convert to a PDF file. A more advanced version of OCR is used for taking notes by hand on your tablet or smartphone. This software is able to learn from your own handwriting. Another application is actually reading. I'm talking about systems that are supposed to understand written text in front of them. A nice example would be a robot that reads books out loud. It has to understand the printed characters prior to converting text to speech. Now, about our project, it's a segment display recognition system, which I decided to call SDR. This is not a formal term, I just came up with the name, but if you do a web search for systems that recognize digits from 7-segment displays, you'll find lots of interesting projects and research papers. The objective here is to recognize digits from a single 7-segment display like this one. The letters shown inside each segment are their standard names, A through G. We are all familiar with these displays. And these are the most popular digit patterns for 7-segment displays, and they are the ones we will use for training our neural network. So again, the objective is to recognize multi-digit numbers by first recognizing the digits separately. This is a suitable task for a neural network because the input may come from a picture or a camera used by some computer vision system. The software will extract the brightness of each segment and send that 7-number vector to our neural network. We'll take it from there. Since we'll receive the brightness of each segment, our neural network will have the chance to generalize and guess what a pattern really means. In other words, not all numbers will have a 100% brightness in every segment that's on. Actually, alright, here's a system-level challenge for you. Design your own segment display recognition neural network. We'll give some thought to the design first, so please don't write any code just yet. Instead, try to answer this question. How would you recognize numbers from 0 to 9? Think about the dimensions of your multi-layer perceptron. We already know that we want 7 inputs because we'll receive 7 brightness levels, one for each segment, but try to answer these questions. How many inputs and outputs would you use? How many hidden layers and how many neurons per hidden layer would you use? And also try to think how you want the data to be presented at the output of your neural network. Your solution should be a diagram like this one, showing the inputs, the neurons, their connections, and the outputs. Don't worry about showing the bias inputs. How did you do? I came up with 3 plausible solutions for this single-digit SDR neural network. The first has 7 inputs and 1 output. The second has 7 inputs and 10 outputs. And the third has 7 inputs and 7 outputs. Let me tell you what I was thinking when I designed each of them. My first network has 7 inputs, 1 hidden layer with 7 neurons, and 1 output. In fact, all 3 designs have just 1 hidden layer with 7 neurons. My thinking was to allow each segment to affect 1 neuron exclusively if needed. You could have used more or less neurons in this layer, and you could have used more hidden layers. Now, since I only have 1 output neuron, my output will be a real value between 0 and 1, so some calculations have to be made to output numbers from 0 to 9. I was thinking of assigning buckets to encode each digit. For example, anything from 0.1 to 0.1999 many nines will correspond to 1. Anything from 0.5 to 0.5999 many nines will correspond to 5. That is, the recognized digit will be the truncated integer of 10 times the output. Although this is a valid model, a one-output neural network for a multi-class problem is almost always avoided and discouraged. The reason is that it has many setbacks, and the alternatives are much better at little to no cost. Here we have 2 things that are wrong about this approach. First, we are solving a classification problem with a regression tool. The sigmoid function in the output makes it a binary classification tool. So assigning the output values to uniformly distributed buckets in the output domain is not an easy task with the nonlinear sigmoid because those buckets aren't so uniformly distributed for the input domain. The reason for this is that we are using a good tool for the wrong problem. In other words, we are drilling with a screwdriver. It may get the job done, but our drill would do a much better job. Here's the second reason not to use this model. We are assigning the values to consecutive buckets in the output. That is, we are mapping our unrelated classes to sequential values as if our classes needed to be sorted that way. Yes, in our segment recognition system, we are using digits, but they don't have to represent their values. They're just symbols for now. Think about it with a different example like this one with 4 classes: bird, dog, cat, and mouse. There's no real reason to say that dog is greater than mouse or bird is greater than cat. So with this mapping, we're constraining our classifier to satisfy an additional and useless requirement. This adds complexity to the learning struggle of our neural network. So this is my first system. Once again, this is a valid model, but there's a universally accepted alternative. My second network is that alternative. It has the required 7 inputs and 10 outputs in a technique known as one-hot encoding. What this means is that each of the outputs represents one of the output classes, and so each of the output neurons will raise its hand, if you will, whenever we enter the pattern that neuron is sensitive to. The way for us to show the recognized number would be to report the class of the output with the greatest value. Notice that we've solved both problems of the previous model. All of the classes have their own independent neuron, so they're not constrained by each other. How's that for a convenient alternative to We have come to our final challenge. It's time to train the segment display recognition neural network you designed. So here's what you have to do in this challenge. Create the neural network you just designed. Train it, either using the provided datasets or your own. Now, my dataset is the very minimum. We'll simply train the network with the 10 ideal patterns. So you may add your own patterns if you want. Train the network for a large number of epochs. Something between 1000 and 3000 epochs will do the trick. Just like the XOR training challenge, we will not use the validation or test phases. Finally, test the neural network with your own samples. Do this in the text terminal to keep it quick and simple. Now, after I show you the text-based solution for this challenge, I will show you 3 separate applications that implement the 3 neural networks we saw earlier, using sliders, buttons, and other GUI controls. And you'll have the chance to use your neural network in these demos if you'd like. So remember, you are only expected to test your neural network in the terminal. That said, if you would still like to make your own GUI, please feel free to do so. So as usual, I have prepared some testing code at the bottom. Here you should be ready to write your own code, but I have provided the very minimum training set for the 3 models I showed you in case you decided to implement one of them. Be aware that these code snippets aren't functional on their own, so you'll have to write the missing code if you want to use them. If not, feel free to delete them from this file. So starting at line 124, we have a piece of code you may use to train the 7-to-1 neural network. Notice that the patterns in the input are entered with zeros and ones. Take a moment to read these lines and verify that each sample corresponds to the number in the comment at the right. So for the labels, notice that I'm assigning each pattern to the midpoint of its intended bucket. For example, the pattern for 7 is mapped to 0.75. Starting at line 140, we have the patterns for the 7-to-10 neural network. The patterns are the same as before, but notice the nice identity matrix look of the Let's see my solution. This program will train each of the 3 systems, and then it will read an array of 7 floats from the terminal to show us their outputs. In line 121, we are obtaining the number of epochs from the user. Then we initialize MLP1 as the 7-to-1 system, MLP2 as the 7-to-10 system, and MLP3 as the 7-to-7 system. Next, we have the provided training code for MLP1, then for MLP2, and for MLP3. Then, starting at line 176, we have a loop where the input pattern is read from the terminal. The array must be entered as a series of exactly 7 values corresponding to the segments A, B, C, D, E, F, and G, all separated by spaces. When a negative value is entered, the program ends. So the body of the loop prints an interpreted version of the output for each system. Look at line 182 for the output of the 7-to-1 system. Notice that I'm multiplying the neural network's output by 10, and then printing the truncated version of that number. That is, an integer between 0 and 9. In line 185, we have the output of the one-hot encoded 7-to-10 system. Here I'm printing the index of the highest value in the network's output. This is easily achieved with the argmax function. And for the 7-to-7 system, in line 188, I'm printing a rounded version of the output array. So we will only see zeros and ones. Let's see it all working. First, we are asked for the number of epochs to train the neural networks. Let me enter 3000. Now we wait. Remember that each system is being trained for thousands of epochs, so this will take a while. Now we get to enter patterns to the 3 neural networks. Let's start with an easy one. The pattern for number 1 is 0110000. There you have it. The 7-to-1 network recognized number 1. The 7-to-10 system recognized 1 as well. And the 7-to-7 system outputs the same input pattern. Let's see all with a graphical user interface to allow you to see the neural network working as you tweak the input values. Please note that you cannot run these demos in the GitHub codespace because of the GUI elements. So if you'd like to follow along, you'll need to have Python installed in your computer along with NumPy and tkinter. What you are seeing right now is my local installation of Visual Studio Code. The source files are called sdrnn721, sdrnn7to10, and sdrnn7to7.py respectively, and they all import mlp.py, so you may try your own neural network with them. For your convenience, all these files are included in the code for the 3 demo videos. If you would like to read through these source files, be advised that they contain a lot of code to implement the graphical stuff. So you may be interested in 2 functions that deal with the neural network. These functions are present in all 3 implementations. The first one is called train callback, and that's where the backpropagation happens. You can see it here starting at line 73. The second one is called run-ANN, and that's where the neural network is run once every time the user changes the input controls. I'd rather show you the rest in the running application. Let's start with the 7-to-1 model. So first, let me tell you about the user interface. At the left, I created a set of 7 sliders to act as the segments in the input. Moving them causes their color to simulate becoming brighter. At the right, we have parameters and results. You may enter the number of epochs to train next, which will happen when you press the button. Then, as results, the application displays the last reported training error, the number of epochs trained so far, the raw output value, and finally the recognized number in a big, bold font. So let me train this network in steps of 100 epochs. Pay attention to the training error as it drops. I'll keep training until the error drops below 0.0001. In other words, when it reaches 4 zeros to the right of the decimal point. As you can see, I have trained this network for 1700 epochs. Now, none of these applications has a valid excuse for not recognizing a trained pattern. So all numbers from 0 to 9 must be correctly recognized. Let me show you a few patterns. Here's number 1. Here's number 4. And number 9. Not recognizing either of them would have been unacceptable. Okay, recall I mentioned something wrong about this model. Now let me show you what that is. Let me enter number 7. Yes, it's classified correctly, but now let me change the input values from total zeros and ones to nearly zeros and nearly ones, and let's see what happens. Does this look more like a 6 than a 7? How about this? And this does not look like a 5 at all. With this behavior, we are witnessing a system that is not very good at generalizing. Now let me show you something. Notice that we have the same controls except for the raw output, which is now showing us 10 raw outputs. That is, one output per class. So remember, the output with the highest value will be the one reported as the recognized number. Let me train this network for 1000 epochs. So again, let's see if it recognizes number 3 correctly. How about number 5? Now let's see number 7. So far so good. Let's see how tolerant to small changes this classifier is. As you can see, I am entering nearly zeros and nearly ones. And the recognized number remained a solid 7. So as you can see, this is way more tolerant than the 7 to 1 network. And now for the 0 to 8 and back test, let me set up the segments. Here we have the pattern for 0. Now, before I slide the middle segment, remember that there's no reason for the output to show anything other than 0 and 8. So let's look at the 7 to 7 network. Now I'm not showing the raw outputs any longer, but another set of sliders simulating an actual LED 7-segment display. This display will show us what the neural network infers from the input. Again, if the input is a valid pattern, then there is no excuse for outputting anything other than that pattern because the neural network is very well trained. The interesting part is the output we get when we enter an invalid pattern. Let me train the network for 2000 epochs. Once again, let me test the network to see if it's working correctly. So let's enter number 2. Then number 6. And finally number 1. Great. And now I want to show you a nice example of how the neural network struggles to get the incoming pattern right. I'll show you an invalid pattern now. The pattern at the left is very special because depending on the state of the bottom left and the bottom right segments, it could be 2 or 3. If both segments are on, the pattern is invalid, as well as when both segments are off. So at this point, both segments are off, and the output is showing something that looks more like a 3 than a 2. But notice as I slowly increase the brightness of the leftmost segment, the output becomes more confident of seeing a 2 and less confident of seeing a 3. So you will see those two sliders at the right go in opposite directions. In fact, whenever I move either of those sliders, the sliders at the right will be having a tug of war towards the correct pattern. Like I said, the interesting part is the output we get when we enter an invalid, or rather an incomplete pattern. This behavior is similar to a text completion application. For example, if I turn every segment off, it suggests something that looks like a knife. Of course, there's so much more you can learn about neural networks, so as next steps I suggest the following. Put your models to the test by using training, validation, and testing datasets. Assess your neural networks for usual problems like overfitting and underfitting. Experiment with more hidden layers and with more or less neurons per layer. And you may want to try all of these things with a readily available neural network tool like TensorFlow or PyTorch instead of writing the code by yourself. Thank you for taking the course. Now I'll leave you to get to work on your next neural network application. Till next time.